Hello, everyone. So today we're going to start lesson 4, which is kind of a two-part lesson. Lesson 4 and 5 are going to go together. We're going to deal with laws of logarithms. And then today we're going to deal with laws of logarithms with respect to exponential equations. Then tomorrow we'll deal with the laws of logarithms with respect to logarithmic equations. Okay, so our purpose today is we want to introduce some of the laws to you. These work very similar to identities that you did with trig. Laws are really just identities. And as we show them to you, they will be on a formula sheet for you as well. So you will have access to them. You don't have to memorize any of this. Okay, so we'll start by introducing the concept, and then we'll go through some different exponential equations that we would solve for. Remember yesterday we ran into a snag when we were solving for exponential functions. The tool that we did yesterday was we got the bases the same on both sides. But then we ran into a snag near the end of the lesson where I was faced with a question that we couldn't get the bases the same. So when we can't get the bases the same, we're going to turn to our newfound knowledge of logs, which you don't have yet, but you'll have in about a half hour. So great start. Okay. So today we learn how to perform operations on logarithms and why they will be useful to us. Solving for unknown exponents when the bases can't be the same. Remember that a logarithmic function is the inverse of an exponential function. That is to say that a log undoes our exponent laws. Okay, so how does that work? Well, when this mathematician here created what he called the logarithm, his goal was to turn multiplication into addition. Now, why would you want to do such a thing? Well, let's go inside his head for a second. Think this through for a sec. Multiplication of many numbers is super complex. If I asked you to look at that and say, hey, I want you just to multiply that in your head, that's like near impossible. You can't do that. You have to get out a piece of paper. It would take you like forever. But addition actually isn't as hard as multiplication. If that was lined up properly, you could probably add those together without a calculator fairly easy. So the thought was, okay, how could I turn multiplication into addition instead? And this is kind of the basis for it. Think about this for a sec. 8 can be written as 2 times 2 times 2. 2 cubed is 8. Okay, and so the basis of this is to say, okay, well, let's take log of 2 times 2 times 2, and let's be able to expand that out and call it log 2 plus log 2 plus log 2. So we took multiplication, that 2 times 2 times 2, and we switched it to addition. Okay, and doing that actually created 3 different log laws that we're going to talk about, and these are them. So we have a multiplication law, we have a division law, and we have a power law. The multiplication law says that log base A of B times C. So anytime that you have factors in here being multiplied together, you can expand that out to be log base A of B plus log base A of C. So multiplication can be expanded out to be separate log addition. Likewise, division can be expanded out to be separate subtraction. And then we have the power law, which says if you have an exponent on the thing you're taking the log of, so that C is an exponent on B right now, we can actually move that to the front. So it'll be C times log base A of B. Now, there is a couple disclaimers to talk about with these guys. First of all, for every one of these laws, A, B, and C have to be greater than 0. And you want to be careful with the power law. Sometimes there will be questions where you see it in this form instead, where that C is actually an exponent on the whole thing. It's not an exponent on B. Rather, it's an exponent on log base A of B. Okay, that's not the same as being an exponent just on B. Okay, so it's this guy here that the C can come to the front. This guy here, the C cannot come to the front. So you just have to be careful of that guy. Okay, so the power law is incredibly helpful to us today. This is what we're going to spend some time on for the next few examples to show you how we can use it to solve for unknowns that we couldn't do yesterday. Okay. Okay, so in our first example, it says solve the following algebraically. Now, you may look at this and you say, hey, Hill, you're an idiot. I can make the basis the same right away. Yes, we wanted to start with one that you could try both ways to show that it still gets the same answer. You could look at this right now and say, hey, 4 can be written as 2 squared, which means x has to be 2. Okay, not the point. I'm going to walk you through how to do this using logs instead, so that when the next example comes where we can't write them as the same base, you're going to be good to go. Taking the log of a number is a mathematical operation. Just like squaring both sides, or just like squaring a number, or just like adding 5 to a number, or whatever. So the point I'm trying to make here is, with algebra, as long as you do the same thing to both sides of the equation, you're not changing the equality statement. You're not affecting that equality statement. So just like I could add 5 to both sides, I can take the log of both sides. Taking the log is just a mathematical operation. So as long as I do it to both sides, I'm not changing the equality. So that's what I'm going to do. I'm going to take the log of both sides, and that'll be log of 2 to the x equals log of 4. Now I'm just writing log. We mentioned this a couple lessons ago. What base am I at? I'm hoping you all just screamed out, I'm base 10, right? This is the common log. And so when it's base 10, I don't actually have to write the 10, but just as a note, remember that log x is log base 10x, okay? If you just see log, you're in base 10 right now. Okay, so now what I'm gonna do is I'm gonna use that power log law, a reminder that the power log law tells me this exponent here can come to the front. So I can now write that as x times log of 2. Well, now, if the whole point is I'm trying to solve for x, log 2 is just a number, so I can divide both sides by log 2. Okay, so x equals log 4 divided by log 2. And then if you type that in your calculator, and I would really like you to do that for a second to prove the point, log 4 divided by log 2 does in fact equal 2. Okay, if you are an older TI or a white Casio, make sure you're closing the brackets that get opened up when you press log. If you're a newer TI or a newer Casio, actually with TI for sure, you always have to close the brackets. The Casio, you don't have to open a bracket, so you can just go log 4 divided by log 2. Okay, so there's your first one done. Let me just clear that drawing, and we'll start in on 5 to the x equals 2. Now you're going to do this the exact same way. The point we want to make here is now I cannot make the bases the same. I can't make a 2 become a 5. I can't make a 5 become a 2. So I'm just going to take the log of both sides. So if I log both sides, this x as an exponent can now come to the front, and that will give me x times log 5 equals log 2. And then I'll divide both sides by log 5, and I get x equals log 2 over log 5. Now, I know I've said this in other notes before, but there has been no rounding instructions here. If there has been no rounding instructions, that means you need to answer an exact value. This is your answer in exact value, okay? As soon as you type this into a calculator, you're gonna get an irrational decimal. Now, I still want you to type it in your calculator because I want you just to have practice making sure you've set things up right. But this is the exact value answer if you're being asked this on a test. But plug that in your calculator and make sure you are arriving at approximately 0.43. Okay, so I am going to give you the decimal approximations for the next couple of examples, not because I want you to do that, but just because I want to make sure you're typing it in your calculator correctly if you were to get to that stage. Okay, so the next guy is 7 to the x plus 2 equals 50. Again, I have an exponent with a variable, okay? We always end up introducing logs because I'm trying to solve an equation where I've got a variable locked inside an exponent, okay? There are now 2 ways we can get out of that. Either we can make the bases the same and then pull the exponents out and solve that way, or now we know we can take the log of both sides. So I can't make the bases the same, so I'm going to take the log of both sides. Now this x plus 2 will come to the front. Sorry, I got distracted there because the garbage truck just drove past my house, just in case you want to know where my eyes went there. Okay, so the x plus 2 can come to the front. So I have x plus 2 times log 7. Now, remember that log 7 is just a number. So what I need you to see here is this is the distributive law. This log 7 will get multiplied by 2, and the log 7 gets multiplied by the x. So that's going to give you x log 7 plus 2 log 7. Here, I just decided to get rid of the log 7. Sorry, I guess the garbage truck was still throwing me off a bit. I could have distributed that fine, and I will have to do that in another example. But for this one, if I'm trying to get x by itself, that's the only spot x is in, so there's not really any point in distributing it in when I can just divide both sides and get rid of it that way. So good conversation to have either way. So that leaves me with x plus 2 equals log 50 over log 7. So all I chose to do here is at this stage of the game, this is x plus 2 times some number. I got rid of that number just by dividing both sides by log 7. Okay. Now, I still don't have x by itself, but it's easy to do. I just subtract 2 from both sides. So I get log 50 over log 7, subtract 2. Again, that would be your exact value answer. Plug it in your calculator just to make sure you're pressing the right buttons. You would get an approximate answer of 0.01. Okay. Next guy, 2 times 5 to the x equals 7. Again, the 2's in the way right now, so the first thing I want to do is divide by 2. That'll give me 5 to the x equals 7 over 2. Now, I want to get it in, I want to take the log of both sides. I can't get the bases the same. So when I can't get the bases the same, I go and take the log of both sides. Log of 5 to the x equals log of 7 over 2. Now my x can come to the front, and then I'll divide both sides by log 5. So I end up with log of 7 over 2 divided by log 5. Plug that in your calculator just to make sure you can get the right approximation, but this is the exact value answer. If this was all the question was asking you to do, this is your answer, okay? But for fun, plug it into your calculator. You should get an approximate answer of 0.78. Okay, now, this one's a little different because I have an exponent on both sides. My process is the same though. I'm still going to take the log of both sides. It just gets to be a little messier of a question. But reminder, with life and with math, there's always beauty in the mess. So I'm going to take the log of both sides. Now, I've got this exponent that can come to the front, and I've got this exponent that can come to the front, okay? Now, this is what I was thinking about a couple of minutes ago when the garbage truck went by. This guy here is going to have to get distributed, okay? Now, the reason I want to distribute it right now is because I see this, like the reason this is different than the previous question is I see an x here and I see an x here. So I'm not ready to get x all by itself here because x is in several different spots. So what I need to do algebraically is I need to get rid of all the brackets, and then I need to bring all the terms that involve x onto one side of my equation and all the terms that don't involve x onto the other side of the equation. The only way to do that at this point in time would be to distribute. I could divide by log 3 on both sides, but in this example, that's actually going to make my life a little messier than it has to be. So I'm going to do the distributive law instead. And that's going to give me 5 log 6 equals 2x log 3. I multiplied the 2x by log 3, and then the negative 1 by log 3 will give me negative log 3. Okay, so now I need to take this term here, and I need to bring it over to the other side so that I have all my x's on one side. So I'll essentially just subtract that term. So that'll give me 5x log 6 minus 2x log 3, and then I'm left with negative log 3 on this side. Now, I can't put these guys together, but what I can do is I can see that both of them involve x, so I can just factor that x out. If I factor the x out, I'm left with 5 log 6 minus 2 log 3, and then that'll equal negative log 3. Now, Yes, this is this messy pile here, but it's just a number. So this is just a number times x. If I want x all by itself, I divide both sides by that number. When I do that, I end up with x equals negative log 3 divided by 5 log 6 minus 2 log 3. Now, if you were looking for an exact value answer, you're done. This is lovely. To make sure you're a good button pusher though, just plug that into your calculator. If you have an older model calculator, just make sure that that bottom has its own set of brackets around it. You should get an approximate answer of about negative 0.16, okay? Now again, don't miss what we did. What does this answer mean? It means if I was to plug it in for x right here, and if I was to plug it in for x right here, that is the one value for x that would make this statement true. Okay, very similar question. I have exponents on both sides. So I'm gonna log both sides and going to go through the process. I would love it at this stage. I've walked you through several of them. This would be a good time to pause me, shut me up for a couple minutes, you try it yourself, and then come back and we can compare answers. So what I did was I took the log of both sides. I'm gonna apply my power law, so this x will come to the front, the 2x minus 1 will come to the front. This is log 12. Log 12 is just a number, so I distribute it to the 2x and I distribute it to the negative 1. I need to get all my x's on one side, all my non-x's on the other side. So I'm going to take that 2x log 12 that you see here, I'll subtract it from both sides so that it ends up on the left side. I now have two terms on the left side that both involve an x, so I'll factor the x out, and that would leave me with log 7 minus 2 log 12 equals negative log 12. And then divide both sides by this log 7 minus 2 log 12. That would be the exact value answer. And the decimal approximation would be 0.82. Okay? All right, so one more law that we want to talk about now. There's one more step that we could use to simplify our previous answers. We can actually write all of our previous answers as a single logarithm. To do this, we use this other law called the change of base law. Now, this is also on your formula sheet, and I just want to kind of unpack what it means before we explore things here. So log base b of c equals log base a of c over log base a of b. Now, what that means is if I have any sort of log, let's just pick, I don't know, log base 2 of 3, okay? I can change this guy to any base I want. Pick a number. Okay, 17 was the first number I heard. Think that through for a second. Okay, so if I want to change this to base 17, this would become log base 17 of 3 over log base 17 of 2. So I changed it to the base I want, and then on the top of my fraction is what I was originally taking the log of, and on the bottom of my fraction is what the original base was, okay? Now, this is kind of pointless. Why would I ever want to change this to log base 17? There's nothing I can do with a base 17, but there is something I can do with a base 10. Log base 10 happens to be a button directly on my calculator. It's the LOG button. So what I could do is I could say this is log 3 over log 2. Okay? Now, what I want you to see here and what we're about to unpack, we're actually going to use this to unpack the last law in a minute, but everything in math is bidirectional, right? So if I can go from here to here, that also means I could go from here back to here. And that's what I want to take a look at. So before we look at these questions one more time, just think this through for me. What I want you to understand, what has just happened, what I'm very excited about, is if I had log 5 divided by log 3, I now know that that could have been written as log, my original base would have been 3, and my original number that I was taking the log of would have been 5. So log 5 divided by log 3 is the same as saying log base 3 of 5. Okay, so now what I want you to do is I want you to look at the first 4 examples that we did together. And I want you to take that exact value answer, and I want to see if we can switch it to a form like this for a sec, because we're going to try and decide or develop one more formula. So if you looked at the 2 to the x equals 4, you ended up with an answer that said log 4 over log 2. Now, based on the conversation we just had, that means I could write that as log base 2 of 4. The second one we did was 5 to the x equals 2. We got an answer that was log 2 over log 5. Based on the conversation we just had, that means it could also be written as log base 5 of 2. Over here, we got an answer of log 50 over log 7, subtract 2, and then log 50 over log 7, based on the conversation we just had here, can be written as log base 7 of 50. And then the subtract 2 is still there. And then this guy here, the 2 came over, so it was 7 over 2, and we got an answer of log 7 over 2 over log 5. Based on this conversation, that means it could be written as log base 5 of 7 over 2. Now, here's what I want you to look for. I want you to decide, is there a way that I could go from here directly to here? Is there a way that I could go from here directly to here? Now, these two are the simplest ones, so let's just deal with this for a second. What I want you to notice is a couple of things. Number one, 2 was the base of the exponent, or 2 is the base of the power, okay? 2 is the base of the log. 5 was the base of the power. 5 is the base of the log. So I guess there's a lot happening at once here, and I don't want to rush you through this because I want you to see these connections. This 2 to the x equals 4 is written in what we call exponential form. This x equals log base 2 of 4 is written in what we call log form, okay? But they're the exact same thing. They are equivalent statements. And because they're equivalent statements, what we're trying to do right now is we're trying to say, hey, is there a way I can just convert between the two statements? Can I write something that is in exponential form directly into log form instead of just taking the log of both sides? Likewise, could I write something in log form, or sorry, could I write something that is in log form into exponential form? Now, what we've noticed is that the base stays as the base. So the base of the power becomes the base of the log. Now, these other two guys have jobs. Right now, the x is locked. I like to think about it as locked and free. So the x is locked, and when I switch forms, he becomes free. He's all by himself now. He's not part of an exponent anymore. The 4 was free. He's now locked. He's locked into the log, okay? So one of the things you're gonna hear me say over and over and over again, when we're switching forms, you kind of have to think about 3 statements. The base stays as the base. So the base of the power becomes the base of the log. If I was locked up, I'm now free. And if I was free, I'm now locked up, okay? So let me clear all that. Same thing here. Take a look at this for a sec. The base became the base. If I was locked, I'm free. And if I was free, I'm locked. Okay? The base became the base. If I was locked, I'm free. Now we freed it and then we subtracted 2. And if I was free, I'm now locked. the base became the base. If I was locked, I'm free. And this ended up being 7/2. That was free, now became locked. Okay. So the last law of logarithms, oh, let me just take that off for a sec. The last law of logarithms is this guy here. It says y equals b to the x is the same as x equals log base b of y. Again, just to bring it home, the base becomes the base. If I was locked, I'm now free. And if I was free, I'm now locked. And it works going the other way too, right? The base becomes the base. The dude that is locked becomes free, and the dude that is free becomes unlocked, okay? So I've written that here for you. The base becomes the base. If you're locked, you're free. And if you're free, you're locked. And that's bad grammar. That should be apostrophe RE. I'll fix that before I PDF this. Okay. This is an equivalent statement. Although these two look completely different, they are the same thing. They're essentially an identity. They're just written differently. So why wouldn't this work as well on the last two parts? You notice I only asked you to do this for the first 4 parts, but we actually had 6 questions that we did there together. The last 2 were just a little trickier because the exponent, there was an exponent on both sides, so it doesn't transfer as easily. It is something you can do, but you have to be a little bit more conscious of some other log laws that we haven't really unpacked yet. So it's just a little bit more complicated. When you get to a situation where you have exponents on both sides like that, I think the easiest thing to do is go back to the thought of taking the log of both sides and solving that way. Okay, so state the domain of each of the following and then solve. So I got 21 to the x equals 13. Remember, if you're trying to think about the domain of this, you're really just thinking about what can x be. X can be anything. So we say the domain is negative infinity to infinity, or x is a member of the reals, whichever one you like to write better. Now, I'm just going to switch this to log form. The base becomes the base, so I'm going to be looking at log base 21. Dude that was locked is free, so this should be x equals. Dude that was free should now be locked. So it's the 13 that gets locked into the log. So this would be rewritten as x equals log base 21 of 13. Now, here's the nice thing about this. I'm done. This is it, okay? This is my exact value answer. Now, if you were trying to get a decimal approximation, I don't care about it, but if you were trying to get a decimal approximation, you can put that in your calculator. Either you use this change of base identity that we were talking about, which no matter what model of calculator you have, that's probably the easiest thing to do. You should be able to just look at log base 21 of 13 and say, hey, I can just go log 13 divided by log 21, and that'll tell me my decimal approximation, okay? If you like fancy buttons, if you are a gray or newer Casio, what you can do is you can press in your calculator screen, you can press the math button, and then you'll see F2 says log AB. If you are a white Casio, you would need to press option and then go to calc, then go to more options, and then you'll see log AB as F4, okay? Then if you are a new TI, you can press the math button and go up to, and you'll see log base. If you're an older TI, older TIs don't have that in their operating system, so you would have to just do the change of base. So you'd go log 13 divided by log 21. All of you though, really, I think that's easier just to go log 13 divided by log 21. But if you like to play with buttons, go ahead and figure that out. Your answer should be, for 21, 13, your answer should be 0.84248000309. Just knew that off the top of my head. Not really, there's a calculator right below the screen. But yeah, so just check that if you want to make sure you're inputting things right. Okay, next guy, same thing, 15 equals 12 to the x. My x is locked up as an exponent, so in order to unlock it, I'm going to switch it to log form, okay? Again, I want to make the point, when I switch from exponential form to log form, I'm not changing anything, okay? These are not inverses of each other. I'm doing an inverse operation instead. So 15 equals 2 to the x, and x, sorry, I forgot about the domain. Domain, again, is real, so negative infinity to infinity. 15 equals 12 to the x, and x equals log base 12 of 15 is the exact same thing. They are equivalent statements, okay? No difference between the two of them. One is just written in an exponential form. One is written in a form that involves an exponent. The other is written in a form that involves a log, okay? And the nice thing about writing it in the form that involves the log is that's my answer. I have solved for x. I have x all by itself, so we're good to go. Okay, this guy, again, the domain, x can be anything I want here, so negative infinity to infinity. I'll have to divide both sides by 2 first, and then I switch it to log form. Base becomes the base, so I'm looking at log base 8. The 13 over 2 was free, so he's now locked. The x was locked, so he's now free. So I'm looking at x equals log base 8 of 13 over 2. Again, I'm leaving it here because that is my exact value answer. Okay, here we're faced with exponents on both sides. So just as a reminder, if you're faced with exponents on both sides, you don't want to switch forms here. You want to take the log of both sides and go through that. Great time to pause me and check to see if you know what you're doing. You try this, then come back. Welcome back. Domain, some of you are laughing because you never left, but that's okay. Your domain here is negative infinity to infinity. I'm going to take the log of both sides. I'm going to use my power log law. So x will come to the front. X minus 2 will come to the front. I have to take the log 2 and distribute it to the x and to the negative 2. I got to take all terms that involve x over onto one side of the equal sign. So I'm going to take this x log 2 and bring it over, factor the x out, and divide by the number that's there. So your final answer should have been x equals negative 2 log 2 all over log 5 minus log 2. Okay, now the last two examples here are a little different because your variable is not in your exponent anymore. It's actually in the base of the power. The easiest way to do this, like if this said x cubed, x to the 3, like, most of you would say, hey, let's cube root both sides, which is cool. And sort of you're going to do the same thing here, but saying let's take the 2 over 5th root of both sides sounds a little onerous. It sounds a little complicated. So instead, what I want you to think about is taking it to another power, okay? If I had, let me just write this on the board here for a second. If I had x to the 3, and I took that to the power of 1/3, okay? That would give me a power of a power, and when I have a power of a power, I would multiply the exponents together. Well, 3 times 1/3 gives me 1, which means it's x to the 1, which means it's just x, okay? So as long as I was to do that to both sides of the equal sign, I won't have changed the equality statement. Just like I can square both sides, or just like I can take both sides to an exponent of 5, I can take both sides to an exponent of whatever I want. So the trick to this is it's the reciprocal. If I multiply a number by its reciprocal, I'm always going to get 1. So when I see x to the 2 over 5, I'm thinking to myself, okay, I want to multiply that, or I want to raise it to a power, sorry, of 5 over 2. So if I took both, the domain is negative infinity to infinity. Sorry, I got so excited I forgot about the domain. If I take that both to 5 over 2, then what happens is this power of a power, I multiply together and it becomes x. So I get x all by itself. Okay. Now, 4 to the 5 over 2, some of you, if you think back to grade 10, you'll be like, hey, I can actually do that in my head because 4 to the 5 over 2 is the same as the root of 4 to the 5, right? When you have the denominator of your fractional exponent becomes the root of a radical. So the root of 4 is 2, and 2 to the 5 is 32. So my answer here actually is 32. Now, if that conversation stressed you out, you have a calculator, you could have just used your calculator and that would have been fine, okay? So in this last example we have, it's going to be the same sort of process, but there is a quick conversation we need to have around the domain of this guy. The domain of the previous one was real. We went from negative infinity to infinity. And the reason was we could do everything there. Let me just go back to that one for just a quick second. What I need you to see here is the denominator is a 5. So I need you to again remember that that means I'm taking the 5th root of something, and I can take the 5th root of both a positive or a negative number. So that's why the domain in this guy was real, okay? If I now just jump back ahead to this conversation, the denominator here is 6, which means I'm taking the 6th root. That's an even root. Anytime you're taking an even root, you can't take the root of a negative number. So in this example, x actually can't be negative, and so the domain becomes 0 to infinity instead, okay? Now, we're going to solve it the same way, though. We're going to take it to the reciprocal. So the reciprocal of negative 5 over 6 is negative 6 over 5. You do want to include the negative in your reciprocal, because remember, when you take a power of a power, you would multiply these guys together, and a negative times a negative will give you that positive 1 that you're seeking, okay? On this side, so that would leave me with x on this side. On this side, there's not a whole lot I'm going to do to clean this up, with the exception of I'm just going to get rid of the negative exponent. Remember that a negative exponent tells you to flip the base. So instead of writing this as 90 to the negative 6 over 5, I'll write this as 1 over 90 to the positive 6 over 5. Okay, and then that will be my final exact value answer. Okay, so that's it for today. What we're going to do tomorrow is we're going to focus on more of these logarithmic laws, but with respect to logarithmic equations. So today, our focus within the log laws was really around the change of base one and the power log law and the switching forms between exponential and logarithmic. Tomorrow, we're kind of add in dealing with the multiplication one and the division one, okay? So try some of these questions for homework. If you have any questions, you know where to find me, and I hope you guys all have an awesome day today. Take care.